Good morning, students. Welcome to the today's class. I hope my voice is audible.
Yes,
Somebody,
sir.
yeah, fine. Thank you. Today we would like to discuss about lecture number 8, in unit number 2, CMOS inverter. Right. So previously we have seen an Nmos inverter. Okay. What we have seen in the previous classes, we have already seen Nmos inverter. Okay, having two possibilities that we have seen. One is resistive pull-up. The second one is depletion pull-up. Right. So these two things that we have seen previously. So we found a basic problem with this approach is more area. Okay. And more power consumption, high power consumption. Okay. High power consumption. And most importantly, we have seen another one is very bad VOL, output low value. That means when we apply the logic high value, when you apply a logic input to logic high value, if you apply, we are not getting the logic low values should be 0, but it is not happening. Okay. So this problem can be avoided most preferably less area. There is no problem that we trace this problem, but the power consumption compared to the resistive mode is less. Okay. Less power compared to resistive load. Okay. And but we are not able to trace the problem called VOL. Here also we are finding the bad VOL. Okay. So therefore fully we have optimized it for area when compared to the resistor, but we are not getting the remaining portions. Okay. Now this problem can be avoided by another approach called another approach is called CMOS inverter. Okay, so that I need to click another color. CMOS inverter. Okay, so what is the idea behind the CMOS inverter is that pull-up should be uh, pull-up is replaced by, or pull-up is realized by an Nmos inverter. Sorry, Pmos inverter. Sorry, Pmos transistor. Pmos transistor. So that's what we need to understand. What is the difference between the Nmos inverter and CMOS inverter? Obviously, in case of Nmos transistor means we preferably talk about depletion type of transistor only because it is advantageous in terms of those parameters. In case of CMOS, we have to realize with respect to the PMOS transistor. Why we need to go for this one? As I mentioned, these are the problems. Essentially, one important point we need to remember. So whether it is a resistive load, okay, or whether it is VN, Vout, VDD, or if it is a depletion mode type of transistor, VDD, and of course, or some other pull-up also we have seen, and enhancement also we have seen. Agreed? So in the previous classes we have seen enhancement also. Enhancement. Pull-up also we have seen, but very bad what kind of NMOS enhancement NMOS pull up, depletion NMOS pull up. Okay, so everything is bad here. Okay, so not at all good, not at all good. So even output high value, output low value, power consumption is all are very bad for that one, that we will not achieve the optimum solution for that one. But area is less when compared to the depletion. The only the advantages here is that area. Okay, so better I need to write in this case this way. So what we can see that, so I'll write it here, less area, there is no doubt, when compared to the depletion type mode transistor, area is less, and power consumption is also less power compared to depletion. Okay, compared to depletion, because depletion mode type of transistor is always on, therefore it's very difficult to control the power consumption. Depletion and very bad VOL, comma VOH, output high value as well as output low value. Both are very bad for that one. So this is what the problems that we faced in previously. Okay, now we are focusing on another one. So we consider this is a this is enhancement, right? Let us consider this an enhancement. It is connected to VDD. It is also connected to VDD. Connect here, and this is called VN here. So whatever the approach that we have seen here is not good. For all these things, there exist short circuit from VDD to ground. So here from short, so when Vn is equal to Vout for all these cases, Vn is equal to VDD for all these cases, what happened? So pull up and pull down both are on. When Vn is equal to VDD, pull up and pull down is on. When Vn is equal to VDD, pull up and pull down is on. That means that, so this structure allows you short circuit path from VDD to ground, that lead to short circuit current. Short circuit current. That leads to power consumption. So this power consumption is called static power consumption. So therefore, there is a static power consumption is existed in these particular structures. So that means that so when you apply one particular voltage, for example, what we can say that, so this is the architecture that we have seen. When the moment if you apply the input voltage is some value, okay, there should not be any kind of, so if you leave it for that one, there should not be any kind of current flow from VDD to ground. So there won't be any kind of current, therefore the current value is equal to 0 means voltage drop is also the current value is 0 means that there is no power consumption at all. So that means, for example, this is on, this is always off. Okay, that is the best choice. Or otherwise, when Vn is equal to VDD, so the upper one is equal to off, lower one is equal to on. So forever it should be something like that. Statically, if you maintain the Vn is equal to 0 for a long time, or Vn is equal to VDD for a long time, they should not be allow any kind of current from VDD to ground. That's what we should apply. That's what we should understand. There should not be any kind of current flow from VDD to ground. So this structure does not allow you a short circuit power consumption. This structure does not allow you the short circuit power consumption or static power consumption, in fact. So this type of approach is very important. But in earlier cases, this is not happened. So for the first case, Vn is equal to 0 is okay, but Vn is equal to VDD. So both the transistor, both the devices, so both networks will be on, right? So in order to avoid this short circuit power consumption, we are going to use a CMOS inverter. We are going to use a CMOS inverter. So Pmos transistor. So in a CMOS inverter, the pull-up network must be realized by a PMOS transistor, not a resistor, depletion, and enhancement type of transistors, right? So let us look at here now what is happening. So reconstruction. CMOS inverter. So just we have to consider a PMOS transistor, something like this. This is a pull-up network, and pull-down network is an Nmos transistor. Okay, so these two are connected here and take a common point that is called Vout. This is connected to VDD. This is connected to ground. These two are also connected to short circuited and connected to VN. So this is what happened in a CMOS inverter. Clear to all of you? We have done the inverter, CMOS inverter. The CMOS inverter consisting of pull-up network is realized by an Pmos transistor. Pull-down network is as usually Nmos transistors only. The VDD and connections are VDD and ground are connected, and connections are shown here, and VN Vout is connected in this way. Okay, that means that in a complementary, what do you mean by CMOS? It's a complementary MOS inverter. C stands for complementary MOS inverter. That means that whatever the pull-down network we are considering here, this is the complemented version that we have to consider. That means that complementation in the sense, if you consider the pull-down network is Nmos, pull-up network, then pull-up network should be Pmos. Okay, if the pull-up network consisting of series connections between the transistors, if you are using, pull-down network must be parallel connection. Parallel, right? Suppose if the connection between the transistors is in parallel, for example, in pull-down network, parallel, it is in parallel, then this must be in series. Agreed? This is why it is called complementary MOS structure. Okay, since only one transistor here we are considering, if instead of Nmos, that means if you are using Nmos, pull-up must be Pmos. But since it is only single transistor, we are not going to consider this one. When we are realizing a more number of transistors, but this is also coming to the picture. Agreed? Now let us see its operation. What is its operation? That means that what happened if some input voltage that we apply, what will happen to another copy? Okay, here let us consider points here. So let us do the same analysis here. So let us consider when Vn is equal to 0 or logic 0, what will happen? When Vn is equal to 0, what is happening to this one? So before going to what happened to the different type of transistors, let us understand some basics related to the Pmos transistors. Okay, so therefore it will be easy for us to understand other concepts. Okay, so before going to this operation exactly, let us investigate one more time for Nmos transistor. Reason of operation of Nmos transistors. Okay, for an Nmos transistor, okay, when VCS value is less than VTN, Nmos transistor threshold voltage, what is the condition of this transistor? It is in off transistor. Whereas for a Pmos transistor, please remember very carefully. Whereas for a Pmos transistor, when VCS value is greater than threshold voltage of a Pmos transistor, then it should be off. Please remember that. It's an opposite to that one. Earlier, I have taken the magnitude without any difficulty, but originally we need to consider in this way. So VGS value is greater than VTP, it is an off transistor. Now, for example, VGS value is greater than or equal to VTN, then we say that the MOS transistor is on. So what about here now? When VGS value is less than or equal to VTP, then we can say that this is a on transistor. Okay, just opposite to this. The Nmos operation is opposite to the Pmos transistor. Means its terminal characteristics are also in opposite fashion. Okay, that's what another point. So once it is on, we need to remember that. When it is in linear, when it is in saturation, when VGS minus up VT, yeah. So it is less than, we say that it is in linear, as everybody knows that. But whereas here is the thing is different. Things are different here. And VDS is greater than VGS minus of VTP. So consider that VTP is negative for the Nmos, sorry, for the Pmos. VTN is positive for the Nmos. Okay. So please remember that points. VTP is negative for the Pmos. VTN is positive for the Nmos. Please remember. So then it is in linear, right? Now again, we need to consider another point. VDS value is greater than VGS minus of VTN, then it is called in saturation. So here we consider VDS value is less than VGS minus of VTP, then we can say that that is in saturation. So these points we should remember. Okay. So for the Nmos as well as for Pmos, this difference should not be forgotten. Because in order to identify the characteristics of the particular structure, these are very important for us. Okay. Now let us apply the same kind of situation to this one also. Okay. So let us understand the operation of the transistor. It's easy now then. So operation. Okay. Now. So I'm going to consider this color. Okay. So let us consider when VAN value is equal to 0, what will happen to this structure? Or logic 0. Or what is the condition of Nmos transistor? As everybody knows that. What is the Nmos? Sorry, what is the Pmos? Let's try right Nmos transistor, right? Nmos. Nmos transistor becomes off. That's what we have studied previously. What about Pmos? What are the Pmos? Pmos becomes on. Pmos becomes on. How can you say that the Pmos becomes on? So I'll write that point here. Okay. And I want to remove this portion because Pmos becomes on. Only Pmos is on. Clear? Okay, now look at here. What are the conditions a transistor should be on for the Pmos? Since we know that VGS value and VTP value we need to consider. What is the VG stands for a Pmos? VC minus of Vs, and this is VTP. So, and also we need to remember that here, since one point we need to write VTN is positive, VTP is negative. Okay, negative value. Okay, now, so what is the VG here? We have applied 0. What is the source? By the way, as we know that this is the source for the Pmos, This is the drain for an NMOS. This is the gate for PMOS. Sorry, this is the gate for PMOS. This is the gate, source, and drain for the PMOS transistor. I think better I need to write here itself. Okay, this should be the source. This should be the drain. This should be the gate. This should be the drain for the NMOS. It's a gate and source. So the source potential for the PMOS should be high. Then only the carriers can travel from the source to drain. Okay. So in order to travel the sources, in order to travel the carriers from in order to flow the carriers, sorry, in order to flow the current from source to drain, the source must be very high. In order to move the carriers from source to drain, the current should flow from drain to source for the NMOS transistor. Therefore, the drain potential is more than that of the source potential. That we should remember that point. Okay. So this point we have discussed previously in the NMOS operation. Now, what is the VDD? VS now? VS is connected to VDD, right? We write it is VDD. What about this value? It's VTP only. So it is minus of VDD, and this is VTP. Which one is the greater? What is the relationship between these two? Consider the typical values. Typical values. The typical value is nothing for VDD is actually a 5 volts that normally considered, and the VTP is minus 0.4. Okay. Now, in this sense, what is the value that we observe? Minus 5. Here is minus 0.4. What is the relationship between these two? Anyone from the class? Is greater than or equal or less than? What is the relationship between these two? Negative quantities we are talking about. Okay. So negative quantities we talk about. Here is the 0, for example, minus 1, minus 2, minus 3, minus 4, something negative axis it is. So is minus 4, minus 5 here. Here is somewhere around minus 0.4. Which one is the higher value? Minus 0.4, or what is the relationship between these two? Anyone from the class? Please respond, or you can write it on the chart box also. Which one?
Minus 0.4 is greater.
Yeah, exactly. So we observe that minus 0.4 is greater than that of minus 0.5. Okay. So it is decreasing from 0 to minus. So if you go beyond the left side, values are less values. If we go towards the right side, higher values are there. Therefore, what is now? This is the condition that we got. So now from this one, what we say that the MOS transistor is on or off. If for PMOS transistor, the PMOS transistor is on. What about for NMOS transistor? I think same thing is applicable here also. Okay, so for the sake of simplicity, I will consider the same notation for the PMOS as well. Sorry, NMOS as well. Okay, same typical values we consider. Here we put it here. So let us consider NMOS transistor. Okay, it is in NMOS. NMOS, what is the operating condition of here? So here also we have to consider VTN, right? VTN. So this is actually what is happening for this one. This should be negative N values that we try, right? So N. So here, what is the source for this one? VC at the 0 potential only we have applied. What is the VDD? Sorry, what is the VS? It is a ground. Okay, ground potential. It is a ground potential. Actually, it is ground. It is 0. That means 0. So typical values, this one is plus 0.4. This plus 0.4. So what is the right hand side expression? This is typical values we consider. This is a 0. This is 0.4. So the expression for this one is less than 0.4. Okay. So less than 0.4 means what is happening for this one? It is in cutoff. Okay. Cutoff, which shows that. Therefore, the PMOS transistor, NMOS transistor is in off mode. So please remember that. So therefore, that is the reason why I have it is an open circuited for NMOS. PMOS is on transistor. Okay, that's what we understand. So whenever Vn is equal to 0, NMOS transistor is off, PMOS transistor is on. Right? That's what we observe. Now the question is that what is the output voltage that we got when Vn is equal to 0? That is what the observation. Can anyone tell me what is the V out for this the device for Vn is equal to 0? Please identify that. When Vn is equal to 0, what is the condition? What is the output voltage? మనం ప్రీవియస్ గా చూసాం మనం ఇంత ముందు. What happened? So here the current from drain to source of NMOS transistor is 0. That's what we identified. Because it's a cutoff means there is no current. But upper transistor is on. That means there is a non-zero current is flowing. So because of this IDS value is 0, the current flowing through this structure is 0. Okay, because of this 0, here also IDSP is also 0. How IDSP is 0? Because of this is series connection. Okay, so now this leads to the drain to source voltage of this transistor becomes 0, which means that the drain potential is equal to the source potential. What is the drain potential here now? Drain potential is actually V out. Okay, what is the source potential for the PMOS transistor? Is it VDD? So did we get V out is equal to VDD in this sense? Therefore now V out is equal to VDD that we got when Vn is equal to 0. Is it clear to all of you? When Vn is equal to logic 0, we got VDD. Are you agreed? Are you agree with this one?
Yes.
Yeah. Now, the second point is that now, okay, fine. What happened to the when Vn is equal to? Now, let us consider the second case. When V out is equal to VDD, let us apply. The second case. The first case. What is the condition for the NMOS transistor and PMOS transistor? Just only have to recall. So let us copy this one. Copy and paste it here. Now the thing is that I'm applying here is VDD. What is the output voltage that I'll get it here? That's what the question. So the same scenario we apply for an NMOS transistor. What is happening for the NMOS transistor? So the alpha on first of all. So for that particular static VDD voltage, what we get? So just we have to, for checking purpose, we are using the VGS and VTN values only. We are checking. Okay, when VGS is equal to 10,000, the gate to source. So the gate is connected to VAN. So therefore, VC minus of VS is VTN. VC is connected to VAN. VT is at source, and VTN. VT is connected to VDD. Agreed? And this is 0, and this is VTN. So what is the typical value is 5 volts? This is 0.4. Which one is greater? The relationship is greater than. Okay, so left hand side is greater than that of the right hand side. Therefore, the transistor becomes on transistor. Okay, so when it is on, so therefore NMOS transistor becomes on. Okay, so therefore NMOS is on. What about PMOS? So again, the same information can be holds here also. So what is the VGS here now? VGS VTP. So it is VN minus of VS and VTP. So VN VZ, sorry VZ. It is VN minus of VS and VTP. What is the VN? VN is actually VDD I have applied. This is also VDD. This is VTP. So this is 0. This is minus 0.4. So which one is greater? What is the relationship between these two? Less than or greater? It is greater relationship, right? It is a greater relationship. 0 is more than that of minus 0.4. Okay. So therefore, what we can observe that the transistor becomes off transistor, right? Therefore, a PMOS transistor becomes off. Okay. So that is what the condition that we have to take into consideration. So therefore, under this condition, what I can say that under that condition, I can remove a PMOS transistor. I should remove PMOS transistor, but I have only an Nmos transistor. Okay. Now, what is the condition for what is the value, output value that I will get it here now? So this value is actually 0. IDS value is IDSP is equal to 0, which in turn makes this IDSN is equal to 0, which makes that VDS of this NMOS transistor is 0, which means that VD value is equal to VS value. What is the VD value for the NMOS transistor? It is connected to Vout. What is the VS here now? It is connected to ground. Okay, it is connected to ground. Therefore, what we observe that Vout is equal to V0, or I can say that the ground value. Is it clear? Is it clear to all of you? So therefore, when VAN is equal to VDD, what I observed, Vout is equal to 0. So this is a very interesting observation when compared to the other things. So here exactly 0. There is no doubt because the upper transistor is completely off. Lower transistor is only on. Okay, therefore the completely we will exactly we will get 0 at this point. Right? Agreed? So therefore, when Vn is equal to 0, we observe that Vout is equal to exactly equal to VDD. When Vn is equal to VDD, which means that Vout is equal to 0, logic 0 or something else. So this is what we can say that the operation can be identified. Okay. So let us depict this information in voltage transfer characteristics. Okay. So let us see the voltage transfer characteristics. Let us see this voltage transfer characteristics. What is the voltage transfer characteristics? Is that you take the x-axis VAN, you take y-axis is Vout. Okay. Now apply when Vn is equal to 0, we expect that Vout is equal to VDD. When we apply the input voltage is equal to VDD, then output value becomes 0. Okay, clear to all of you? Now that means we are moving from higher potential to the lower potential, higher voltage to lower potential, so something like this. So the distinct values only we have considered some 0 volts to VDD. So how it will move? How it will move? Whether this way it is decreasing, this way it is decreasing, in which way it is decreasing? Then we have to understand by simply applying some the physical voltages between 0 to VDD, and we can identify its characteristics, right? by applying the physical voltages from 0 to VDD. That means we thought that it's a logic 0 means a logic 0. 0 means a logic 0 that we have applied. VDD means logic 1 that we have applied. So the discrete information, digital information that we have applied. But what happened if you apply a physical values from 0 volts to 1 volt, 2 volt, 3 volt, 5 volt, something like this, physically some voltage if we apply, how these characteristics can be observed. That means now we can accurately picture that information by applying the physical voltages. Okay, now let us consider the first case. Okay, again, the case number 1 is when Vn is equal to 0 volts. Okay, 0 volts I'm not talking about. In this sense, Vout is equal to 0. There is not, sorry, Vout is equal to VDD. There is no doubt at all. Okay, so in this condition, as everybody knows that Nmos is off, but Pmos is in on, right? When Nmos transistor is on, then అంటే ఎప్పటి వరకు ఇప్పుడు Vout అనేది VDT మెయింటైన్ చేస్తుంది. అంటే Nmos అనేది ఆన్ అయ్యేంత ఆఫ్ అయినంత వరకు అదే మెయింటైన్ చేస్తుంది. ఆర్ అదర్వైజ్ ఐ కెన్ సే దట్ Nmos is as long as Nmos is off, this is maintained. Okay, when this Nmos will come out of that one, off transistor to on transistor, this Nmos is off to on only when the threshold voltage, the VGS value of this VGS value of this this is what VGS of Nmos transistor is greater than the threshold voltage of Nmos transistor. So that means that VGS of Nmos transistor is అంటే VN కదా మనకు కనిపిస్తుంది, అంతే కదా, VG minus of VS kada. VG is nothing but VN, source is at 0. Therefore, simply the VGS of Nmos transistor is nothing but VN only. Okay, agreed? VN only. This is greater than threshold voltage of Nmos transistor. Ainappudu Nmos becomes, then Nmos turn on. Ante kada. Okay. So therefore, the second point that I need to consider here is that, what is the second point here I'm going to consider? When VCSN value is greater than threshold voltage of a Nmos transistor, then I can say that Nmos is on. Of course, Pmos is also on. Other than the second case, that means as long as Vn value is equal to less than Vtn of the transistor, this VDD is available up to that point. Okay, up to that point. When Vn is equal to Vtn, up to the Vtn of the Nmos transistor, the transistor Nmos transistor is off, Pmos transistor is on. Therefore, VDD is old school. Okay. Okay, now very important. When the Nmos transistor is, for example, in this case, for example, so that means that, as we mentioned that, please remember that. So Nmos is off. Okay, no problem. But Pmos, what about the Pmos? Pmos is on. If it is on, we should mention whether it is linear or saturation. That's what we have to mention. So what will happen to that one then? So when the Nmos transistor is on, what is happening here? So I think better I need to put this aside. It's very important. The same analysis we have to apply for any circuit only, but once these fundamentals are clear, this will be. So when the Pmos transistor is on, what will happen? Let us check now. Check that out, sir. Okay, na? What is the Pmos relationship? Since VGS of Pmos transistor and VT Of course, on means we don't want to check this VGSP and VTN value. We have to check for VDS of PMOS transistor, VGS of PMOS minus of VTP. ఇదే కదా రిలేషన్షిప్ అనేది మెయింటైన్ చేయాలి. సో వెదర్ ఇట్ ఈస్ లెస్ దాన్ అయితేనేమో గ్రేటర్ దాన్ అయితే సాచురేషన్, సారీ లీనియర్, లెస్ దాన్ అయితే saturation for PMOS transistor. Then we can consider what is the VDSP? VD minus of VS, VC minus of VS minus of VTP. So what is the value here now? What is the VD for the PMOS transistor? V out. What is the VS? VDD. What is here? VC stands for VAN. What is the VS? VDD minus of VTP. That I'm talking about the PMOS transistor. Please remember that. Don't forget about it. So itla ఇప్పుడు ఈ కేసు నేను చూస్తున్నాను అనమాట. ఇదేమో ఆల్రెడీ V అవుట్ కనెక్ట్ అయింది. సో దిస్ ఇస్ కనెక్టెడ్ టు VDD. దిస్ ఇస్ కనెక్టెడ్ టు VN కనెక్ట్ అయింది. సో ఫర్ దిస్ ఇస్ ఫర్ ద PMOS transistor. Okay. Okay. What is the condition here now? Whether it is less or greater, or what we can say that. As you can see here is that both will get cancelled. VDD will get cancelled. Okay. What is the VN value? Sorry. Of course, what is the V out here now? Before cutting down all these things, let us put the values. What is the V out? V out is connected to VDD, right? That's what we observed. V out is connected to VDD. When VN is equal to 0. So it is VDD minus of VDD. This is what is the VN? 0 minus of VDD minus of VTP. Okay. So that is 0 minus of VDD minus of VTP. What is the relationship between these two? Anyone from the class? Let us consider the typical values. Typical values. VDD is equal to 5 volts. VTP is equal to minus 0.4. What is the value? Relationship. So the right hand side, so left hand side 0 on the mantra, right? Left hand side 0. What about this one? Minus 5, minus of minus 0.4. 0 minus 5 plus 0.4. Therefore 0, this is 4.6. Which one is less than relationship or greater relationship? It is a greater relationship, right? 0 is greater than that of minus 0.46. So which leads to the transistors in linear. But whereas in Nmos transistor, great relationship saturation, but it is in linear current equation. Okay. So therefore, what I can say that here now, Pmos on, but it is in linear. Is it clear to all of you so far? Chapala. So if do you find any difficulty in it to understand up to the VN is up to VTN, Nmos is off, Pmos is on, that too in linear region. Is there any doubt in it? If you don't have any doubt, please we will move to another region. Okay. Now, so after the VN is equal to VTN, after the VN is equal to VTN, what will happen? That means that when VGS is greater than VTN apply chesthe manaki em Nmos em avutundi on ki vellipotundi, Pmos is on lone untundi. Now we should say what is the region of operation of this one, what is the region of operation of this one. That's also an important one. Kani ikkada matram rendu transistor on ayindi. Okay, the point of discussion is here. The point of discussion is here. So up to this point is okay. Now from this onwards, what is happening here? Beyond VN is equal to VTN, or VCS of the Nmos transistor is more than that of the VTN. What will happen? Both transistor becomes on. Again, what we said that so once it is on, we have to concentrate mainly on what about VDS value. what is the VGS minus of VT value. Since I'm talking about NMOS transistor, I'm writing NMOS for all the terminals. Okay. So we observe that what is the for NMOS transistor? I'm talking about NMOS transistor. We took it after that. We will see for the Pmos transistor. Okay. What is the VDS value? VD minus of VS, VC minus of VS minus of VTN. So what is the VD value for the Pmos for NMOS transistor? For Nmos, it's a drain. It is V out. It's a ground. The source is at ground. The drain is at VDD. It's ground VN. What is the drain potential at this point? VDD only. This value is 0. What about VZ? VN minus of 0 minus of VTN. What is the VN value at this point? VN value is equal to VTP actually. VN value is equal to VTP. Sorry, VTN, right? So therefore, this is called VDD. VN is nothing but the VTN, okay, minus of VTN only. So therefore, VDD value and 0 value, which one is what is the relationship is greater? Therefore, an NMOS transistor is in saturation. You know very well. So that means that VDS value is greater than VGS minus of VTH on the property, and NMOS transistor is in saturation. Okay, and the same information is applicable for the Pmos also, but it is in linear only. So again, in this situation, the Pmos is in on, but that in linear. Okay, so the question is a very important question is that one is in saturation, another is in linear. Okay, so therefore what I can write it here is that very importantly the Pmos transistor here, NMOS transistor is here, VDD and the ground. So that means that here the current is flowing here, IDSP. What is the current equation here? Saturation current equation. Sorry, I'm extremely sorry. This is in linear current equation. Linear. What is the current equation here? IDSN. It is in saturation. So therefore, we have to understand the relationship between the IDSP and IDSN. Okay. So therefore here IDSP is equal to IDSN. Okay. So therefore it's simply a parabolic equation, but it is in decreasing fashion. It's a parabolic equation, but it's a decreasing fashion. Why? Because it is increasing, it is decreasing. Okay. So therefore the characteristics are now becomes something like this. So I want to copy these characteristics. Copy. Just I will complete it within 1 minute. Okay. What I can say that here it is a decreasing fashion. Okay, I'll take another color. It is a decreasing fashion. This is a decreasing fashion. Something else, it is decreasing. Where we can say that Nmos is in on, that in saturation. Pmos is also on in this situation, but it is in linear. So again, of course, we know that the Pmos is a linear in the previous case also. That will be continued. Pmos is continued to linear region only. Okay. So that means that as we move on this condition, when keep on increase the input voltage from 0 to VDD, the NMOS transistor is turned into off to saturation. Okay, off to saturation, saturation to maybe linear region, somewhere is it going. Whereas in PMOS transistor, it will coming from linear region to saturation, and saturation to cut off, something like this it will go. I think so, because at the earlier stage what we have seen that in this particular situation The last case, it is a cutoff, Pmos is cutoff region. That means how the movement is going something like this. So the conditions you observe here. So you observe this condition. Nmos is off, Pmos is in linear. The second one is Nmos is changes to saturation, but Pmos remains in the same region. That means that there is a possibility of changing Nmos regions of operations, Pmos regions of operations. So that means something will go from cutoff to saturation, saturation to linear, something like this it will go. So whether it is so in the for Pmos transistor, it is in the linear and saturation, and it will go to the cutoff. That means that its region of operations are changing step by step. Okay, so therefore, what I can say that at what voltage, input voltage, the Nmos will changes its state, as well as Pmos is also changes its state. So that means that నేను ఇక్కడ చెప్పాను ఇక్కడ PMOS అనేది లీనియర్ రీజన్ లో ఉంది. ఇప్పుడు ఈ లీనియర్ రీజన్ నుంచి సాచురేషన్ రీజన్ లోకి వెళ్ళాలి అని అంటే PMOS, దట్ మీన్స్ లీనియర్ టు సాచురేషన్ రీజన్ కి వెళ్ళాలి అని అంటే వాట్ ఈస్ ద కండిషన్ ఆన్ ఇన్పుట్ వోల్టేజ్? వాట్ ఇన్పుట్ వోల్టేజ్ విల్ బి హోల్డ్స్ గుడ్? అలాగే ఒక సాచురేషన్, సపోజ్ కట్ ఆఫ్ రీజన్ లో నుంచి సాచురేషన్ రీజన్ లోకి వెళ్ళాలి అంటే అన్మాస్, వాట్ ఈస్ ద కండిషన్? దట్ ఈస్ VTN అనేది మెయింటైన్ చేయాలి. VCS వాల్యూస్ VTN మెయింటైన్ చేస్తే వెళ్ళిపోతాం. అదే PMOS కి అయితే లీనియర్ నుంచి సాచురేషన్ కి వెళ్ళాలి అని అంటే వాట్ ఈస్ ద రీజన్? సో అప్పర్ వన్ ఉన్నది మనకి ఈజీ అని తెలిసిపోయింది, బట్ లోవర్ వన్ ఉన్నది మనకు తెలియాలంటే ఏం చేయాలి? ఓకే, సో అగైన్ వీ హ్యావ్ టు థింక్ అబౌట్ ఇట్. So we have to go for VDS value of the Pmos transistor, VGS of the Pmos transistor. Only we have to consider. In saturation color, we have to consider that edge of the saturation which matter the circuit. So from that one, we have to get some equation. From that equation, whenever this curve is touching that point, then we can say that it will come out of that linear region to saturation region. Then, so we will evaluate this one. We will evaluate this particular point in the next class, I think. Okay. Or shall we derive this only one particular point at this point? So can you give me 2 minutes? I will complete it, this curve at least. Okay. Okay. Then, so what is the VGS value here? VD minus of VS. VG minus of VS minus of VTP. So therefore, what is the VD for the PMOS transistor? V out only. What is the VS? VS is actually connected to VDD. What is the VG? VAN. What is the VS? VDD for the PMOS transistor, VTP. So here we observe that these two will get cancelled. Then V out is equal to VN minus of VTP. Okay, so this is the equation that holds good, right? By typical values, if you apply, Pn is changing from 0 to VDD, 0 to 5 volts. VTP is equal to minus 0.4. It's a straight line equation, but where it's not the straight line equation. For example, Vn is equal to 0, let us consider. Okay, 0 volts we consider. VTP is equal to minus 0.4, as we know that. What is the V out here now? V out is equal to 0 minus of 0.4, minus of minus plus 0.4 outundi. Idi babu 0.4 outundi. That means that this is available here. 0.4 is somewhere it's here. Okay, so something like this. What is the for the next case? 1 volt applies and 1 plus 0.4. That is called 1.4. So therefore 1.4 something. Therefore this is actually a straight line. So this is a straight line going in this way. So for the 1 volt, so the for Vn is equal to 0.14, something like this, it will go in a straight line. So what is this straight line is we are calling as V out is equal to Vn minus of VTP. So this is the line will decide and a PMOS transistor will enter into the saturation region. So that's what we observe that. So coming down and coming down at this point onwards, PMOS will turn out of that one. Similarly, Nmos is also come somewhere, some other point of the time, it will come out of this one. So up to this point, I hope you clearly understand this situation. This is at this point. Okay. Two regions of operations we have studied. One is that but Nmos and Pmos is off and on. Second one is Nmos and Pmos. And the third point we considered is that when the Pmos will enter into the saturation region. That's what we observed. So we will see the remaining things in the next class. Please read this concept please read this concept. It's very important. Very clearly I have explained. So you can also watch the video also. Thank you very much. Extremely sorry for taking more time.